It's a pleasure to introduce our own Brian Lawrence, who will talk about I forgot your title, Brian, but I know it has to do with algorithmic problems related to Diophantine equations.
Yep, that's it. Thank you very much for the invitation. I'm going to start with a few warm-up problems, so if you get bored or lost during the talk, you have something to think about. The first two are related to kind of the complex, the sort of topology of complex algebraic varieties. So suppose, for example, I consider kind of two-dimensional space over the complex numbers, which is of course really four-dimensional space. And in there, I can look at the set of solutions to some equation, like for example, x squared plus y squared equals 1. And that's going to be kind of dimension 1 over c. So kind of topologically, it has dimension 2. It's a surface. It's an orientable surface. And you know there's a classification of orientable surfaces, just kind of from elementary topology. And so I'm asking you, which surface is this? So I can ask the same question maybe for any polynomial equation I like. The second pair of questions maybe are a little simpler. So consider G R squared mod G squared. That's essentially the torus group. And just take kind of a random generic element in there and look at the cyclic subgroup it generates. And the question is kind of, what does that cyclic subgroup look like if you drew a picture of it? Okay, probably you all know kind of, you've thought about that before, but what happens if instead of R squared mod Z squared, you work with something kind of p-adic instead? You work with, say, ZP squared, where ZP is the ring of p-adic integers. Okay, so I'll let you think about those. So take a picture or a screenshot or something if you want. And I'm going to get started. So today I'm going to talk about Diophantine problems and eventually about algorithms to solve Diophantine problems. I'm going to start with some history because, at least to me, I think Diophantine problems are kind of the fundamental motivating problems behind all of number theory. And so I'm going to start with some kind of early math problems here. So does anyone in the audience read Akkadian? Can anybody read this? So this is a picture of a clay tablet that somebody dug up in Iraq, maybe in the late 1800s. At the time, Iraq was under Ottoman rule, and I understand the Ottoman rulers really didn't kind of regulate the sale or export of things like this. And it was sort of a popular thing for British and American imperialist types to kind of go to the Middle East and maybe pay people to dig up clay tablets in the sand and collect them and ship them back home. And so there are hundreds of thousands of clay tablets like this one sitting around in various libraries in the West. I think this one's located at Columbia now in New York. And what is this? This is basically a table of numbers. And these numbers are more or less Pythagorean triples. So they're solutions to the following problem. You're looking for numbers, rational numbers, x and y, such that x squared minus y squared equals 1, and such that x and y have terminating expansions. Back in the day, they didn't use base 10, they used base 60, so x and y have to have terminating base 60 expansions. So this is essentially the problem of finding Pythagorean triples, maybe with some condition, some sort of divisibility condition on B. And so what the tablet shows, I mean, we don't really know much more about it other than this list of numbers, but clearly the ancients had some kind of efficient procedure for generating solutions to this equation. So here are some other examples of kind of math problems of early interest. I should have said this first one is known as Pell's equation. You fix some integer d, and the question is maybe most interesting if d is positive and not a perfect square. And then you're looking for integer solutions to x squared minus dy squared equals 1. So this was studied in Greece and India, later by the Persian school. The second problem says fix an integer n, find all integer solutions, say, to this equation. And I believe this equation is also kind of classically named after someone from a few centuries ago, but I can't remember who. The third problem, of course, says, again, you fix an integer n and you ask for all solutions to x to the n plus y to the n equals z to the n. And of course, this question is due to Fermat and was eventually proved by Wiles with lots of progress by lots of other people who I haven't named. So in general, I guess I'm trying to convince you that a lot of problems of interest kind of fall into this general family of what's called Diophantine problems, where I give you a system of polynomial equations, either with integer or rational coefficients, and I go asking questions about either integer or rational solutions. So the typical question I might ask is, are there finitely many solutions? Are there infinitely many solutions? If there are finitely many, can you find them all? If there are infinitely many, can you describe them all? Maybe there aren't any solutions at all. And around 1900, Hilbert kind of posed the general problem of saying, well, is there an algorithm that will just deal with any Diophantine problem? So I hand you a system of polynomials, let's say with integer coefficients, infinitely many variables, and I ask you to tell me whether the system has an integer solution or not. And in this generality, the answer is no. I'm not a logician, so what I'm about to say might be completely wrong, but I think the picture is something like you can reduce maybe the halting problem for Turing machines to this Diophantine problem. So if I give you any Turing machine, in other words, I kind of give you any computer program and I ask, will this program eventually halt or not? You can kind of convert that computer program into a system of polynomials, a Diophantine problem, such that the Diophantine problem has a solution if and only if the original problem halts, if the computer program halts. And then it's known kind of for simple logical reasons, there's no algorithm that can decide the halting problem, essentially because of some form of Russell's paradox. I mean, you would take an algorithm, if you had an algorithm like that, you would just feed it into itself and somehow nothing reasonable could come out of that. Anyway, in any case, there's no algorithm in general that will decide whether a Diophantine equation has solutions or not. Are there any questions so far? Okay, now I'm going to bring geometry into the picture. And it's kind of mysterious. It turns out if you have these Diophantine problems, each of these Diophantine problems kind of has an underlying geometry to it, and the geometry actually dictates a lot about what's going on number theoretically. And this is something maybe I find kind of surprising, and so I'd like to draw attention to it. So first of all, I'm asking for solutions to polynomials, right? I'm asking for integer solutions or rational solutions to some polynomial equation. And of course, I can think about that geometrically just by kind of thinking about the solutions to the polynomial equation, if you like, as a subset of Rn or Cn. So for example, asking that first question I started with that tablet from the ancient Near East, that's asking for rational solutions to x squared minus y squared equals 1. It's asking for rational points on this hyperbola. Sorry, I should say a rational point is just a point with rational coefficients, with rational coordinates, right? I'm looking for points on this hyperbola such that x and y are both rational. And so what happens, it turns out that the arithmetic, meaning like the number theory of this Diophantine problem, turns out to kind of depend on the geometry of this variety. So as maybe a simple example of that, well, what's kind of the most simple-minded geometric question you can ask about a variety? You can ask for its dimension. So for example, this hyperbola it has dimension 1, it's a curve. And the first thing to know about kind of modern progress in number theory and in kind of Diophantine geometry is that if you're looking for rational points on a variety of dimension more than one, it's very hard to say anything at all. But if you have a curve, if you have a variety of dimension 1, then you can often solve the problem. Here's an example where the variety has dimension 2. You have the perfect cuboid problem. You're looking for rectangular prisms. A rectangular prism has 3 sides, a length, width, and a height. It has 3 face diagonals, this one, and this one. I assume everybody can see my hand waving at the same time as my shared screen. And it also has kind of a space diagonal that goes through the cube. So there's 7 different kind of lengths associated to a rectangular prism. Of course, they're all determined kind of by the 3 side lengths, A, B, and C. The perfect cuboid problem asks, are there choices of integers A, B, C that make all 7 of these lengths be integers? So this is kind of a generalization maybe of the Pythagorean triple problem. And it's an unsolved problem. It's maybe conjectured that there aren't any positive integer solutions to the system of equations, but it seems to be very difficult. At the risk of ruffling feathers, my impression is that nobody has any idea how to solve this.
Brian, is the hard part here the difference between knowing whether there are finitely many solutions as opposed to none, or is the dish? And is
Thank you. No.
Okay.
The hard part is that I don't think you can even prove that there are finitely many solutions.
And is that understood at the level of conjecture, like, you know, the way Faltings theorem was a Mordell conjecture for a while, so that there's a picture for this, or it's not
sure.
understood
So there's
at the level of conjecture?
There's a
and then
general
I'll stop
conjecture.
for a while.
No, thank you. There's a general conjecture, the Lang-Voida conjecture, which kind of it generalizes Mordell's conjecture. It kind of gives a general condition under which, you know, a higher dimensional algebraic variety would have, you know, only finitely many rational points. And I haven't thought about it hard. I assume this is a consequence. It's a consequence of Lang-Voida that the rational points, that this would only have finitely many kind of integer solutions. And so the conjecture would give you finiteness, and then it's also thought that in fact this particular system has no solutions at all. Thank you. Anyway, my impression with these sorts of problems involving kind of varieties of dimension kind of greater than 1 is that nobody really even has any ideas other than kind of reducing to the curve case, for example. Anyway, for the rest of the talk, I'm going to focus on algebraic curves. So I'm going to focus on situations where the equation kind of has 1 degree of freedom. You're looking for rational points on 1-dimensional variety. So that's a curve, and I'm going to be talking about rational points on algebraic curves. And for algebraic curves, there's a lot more we can say about their geometry. And this comes back to the first 2 problems that I gave you to think about from the beginning of the talk. If I give you an algebraic curve over C, okay, a second ago I was talking over the integers and the rational numbers, right? And now I'm saying, well, if I have an algebraic curve over Q, that certainly gives me an algebraic curve over C. I just kind of say, well, I may as well let X and Y be complex numbers instead. Now, an algebraic curve over C, that's kind of a 1-dimensional complex manifold, but 1 complex dimension is 2 real dimensions. These things are actually kind of surfaces. They're oriented surfaces, essentially because the fact that it's a complex manifold gives you an orientation. In other words, locally, the tangent space at every point is just isomorphic. It's a 1-dimensional vector space over C, and the complex number, the kind of the choice of I as a complex number defines an orientation on the tangent space at every point. So okay, so all these algebraic curves are oriented surfaces, and we have a classification of things like that. It could be a sphere, it could be a torus, which is kind of, you know, a genus 1 surface. It could be a torus with 2 holes, which is a genus 2 surface, and so forth. And then I guess since these might not be compact, you get kind of, in general, you get a genus G surface with some points removed. So that genus, it's a fundamental invariant of the surface. We call it the genus of the curve. As kind of an example of how the genus of the surface is important, if you think back to kind of differential geometry, a surface of genus at least 2 is hyperbolic. Meaning if you have a surface of genus at least 2, you can kind of put a metric on it that has constant negative curvature. A surface of genus 1 is a torus, it's flat, and a surface of genus 0 kind of has positive curvature. So there's this sort of trichotomy between positive 0 and negative curvature, which corresponds to genus 0, 1, and 2. 0, genus 1, and genus at least 2. And this trichotomy is going to show up again on the arithmetic side, on the number theory side. Are there any questions so far? Okay. So just as an example, the hyperbola that I gave before, this curve here, when you view it as a complex surface and you kind of figure out what surface it is, it turns out this has genus 0. This equation defines in sort of two-dimensional complex space over C, this equation defines a sphere missing, I believe, 2 points. And this equation has lots of rational solutions. And that's typical for genus 0 curves. In genus 0, rational points are abundant. The genus 1 situation is more interesting. A genus 1 curve is what's called an elliptic curve. So a genus 1, of course, means you're a torus. So if you're a curve of genus 1, then you're complex analytically or isomorphic to a torus. You're kind of, how to say, a torus, the universal cover of a torus is the plane, and the kind of group of deck transformations is some lattice of translations in that plane. And so you're going to be isomorphic to the complex numbers modulo some lattice. Of course, the isomorphism is given maybe by complex analytic functions and not by algebraic functions. But C modulo a lattice is a group, right? C is a group, a lattice is a subgroup. So the quotient is a group. Any torus kind of naturally, once you pin down a 0 point, the torus kind of acquires a group structure. And that group structure, in fact, is given by an algebraic function on E. There's some algebraic rule that lets you take 2 points on this curve and add them. It makes E into an abelian group. And so an elliptic curve, and this is why kind of the arithmetic of elliptic curves is so rich. An elliptic curve has an algebraic group law. Now we're interested in rational points. So the question is, how many rational points are there on this elliptic curve? How many solutions does this equation have? And the answer is, well, it kind of has a lot. There are infinitely many. But under this group law, the group of the rational points, of course, form a subgroup of kind of all the complex points of E. And the subgroup of rational points is actually finitely generated. So I believe this equation, this equation kind of has one obvious solution that comes from kind of 25 being a perfect square and 27 being a perfect cube. And if I remember right, that solution actually generates all the solutions, all the rational solutions to this equation. So in this particular case, I believe the solution set is kind of a cyclic group generated by that one fundamental solution. Are there any questions about elliptic curves or the genus of a curve? Questions?
I think it's fine, but go ahead.
Okay, great. So what happens in genus more than 1 is the picture is very different. In genus greater than 1, when you have a hyperbolic curve, it turns out the curve can only have finitely many rational points. So this, I think, the first time you see it, this is kind of a really surprising fact. I mean, the genus is kind of a geometric, a topological property. I mean, to even make sense of the genus, we kind of had to pass to the complex numbers. But the genus of a curve actually tells you something about how many rational points it has. So this was first conjectured by Mordell, I think, in the early 20th century. The first proof was by Faltings in 1983. And there have kind of been several proofs, several different proofs that have come out since. So I just want to reiterate, this is kind of a surprising link between geometry and arithmetic. By the way, for the experts in the room, you can replace Q with any number field, and the theorem remains true. And there's a converse. If you're kind of careful how you formulate it in terms of an arbitrary number field, there's a converse to Mordell's conjecture, which says that a curve of genus 0 or 1 will have infinitely many rational points after maybe you have to pass to a larger number field. But for any curve, there's a fixed number field. For any curve of genus 0 or 1, there's a fixed number field over which it acquires infinitely many rational points. Okay. And now with maybe the second half of my talk, I want to discuss the algorithmic Mordell question, which says, okay, if I give you a curve of genus at least 2, sure, we know it has only finitely many rational points. Can you find them? And once you've found them, I mean, of course you can find them, but once you've found them all, can you kind of prove that there aren't any more? So I'm going to talk mostly about kind of an early approach to algorithmic Mordell, actually that predates Faltings' work by several decades. That's due to Chabauty, and that kind of works in calculations on the Jacobian. So in the next few minutes, I'd like to kind of discuss the Jacobian of a curve. So the basic result is that if you have any algebraic curve, you can embed it in a complex torus. So specifically, I have a curve of genus G, which is at least 1. Then for any such curve, I can embed it in a torus of complex dimension G. So that'll be kind of a manifold whose real dimension is 2G. And what is a complex torus? It's literally just c to the G modulo some lattice. Right, a lattice is just kind of a discrete subgroup that's an abelian group of rank 2G. So I have c to the G modulo a lattice. This is just kind of a 2G dimensional torus. And I get this embedding by considering differentials on X. So it turns out if you have an algebraic curve of genus G over the complex numbers, then it has the space of global differentials on the curve has dimension G. And so now I can take these G differentials and I can integrate them. So say I fix a base point, and then for any varying point X on the curve, I integrate from X0 to X. I integrate these G differentials, and that gives me G coordinates for X. So it kind of sounds like now I've defined a map from X into this CG, into this complex vector space itself. But there's an ambiguity because of the choice of path from X to X0. And it turns out this ambiguity exactly kind of gives you a well-defined map into CG modulo lambda. Lambda, if you like, lambda tells you the ambiguity and the choice of path. So if you like, lambda comes from loops on X, or lambda is in fancy language, the singular homology of X. Okay, so as an exercise, if you like, you can try to figure out what this picture looks like, for example, for this curve I've written down of genus 2. Now the Jacobian, the way I defined it before, of course, the curve maps into this complex torus. That map is a complex analytic thing. I took some algebraic differentials and I integrated them. That's kind of very analytic. But in fact, it turns out that the Jacobian has a structure of algebraic variety. And then this map from the curve into its Jacobian is a map of algebraic varieties. If the curve is an algebraic variety over Q, the Jacobian will also be an algebraic variety over Q. And this map will take rational points of the curve to rational points of the Jacobian. So now we might ask instead to study the problem of finding rational points on the Jacobian. Maybe that'll be easier. And then we can ask which of those rational points kind of come from rational points on the curve. Any questions?
Okay, go ahead.
Okay. So the the basic theorem about rational points on an abelian variety. Abelian varieties are just like elliptic curves, like I was talking about a second ago. The rational points on any abelian variety form a finitely generated group. Sorry, an abelian variety is, maybe I haven't given a definition. Maybe I'll just say that the Jacobian of a curve is an example of an abelian variety. So the rational points on the Jacobian of any curve form a finitely generated group. And now the idea is, okay, so here I have the Jacobian of my curve. Inside here, I have the curve embedded in there. I take this finitely generated group of rational points in the Jacobian. Finitely generated means there kind of aren't too many of them. And now I try to intersect those with the original curve, and maybe there'll be only finitely many points in the intersection. So now we come back to the exercise, the second pair of exercises I gave at the beginning of the talk. And I'm going to try to draw my screen, share another screen here to kind of show what's going on. You should see a blank white screen. Do you see a blank white screen?
Yes.
Yep. Okay. So here I have this complex torus. And let's imagine even that the group of rational points just kind of is a cyclic group with a single generator. So there's the generator, and then here are all the multiples of the generator. What will happen in general is that the cyclic group generated even by a single element will end up giving a dense subgroup of the torus. So here I have my torus, which is kind of the Jacobian of my curve. In there I have the group of rational points, and I have the curve itself. And unfortunately, and you should all see that I've drawn something, right?
Yes.
Okay, great. Unfortunately, since the rational points are dense, I mean, it's probably still true that almost all of them kind of miss this curve because the curve kind of has dimension less than the Jacobian itself, but it's not really clear how to prove it. On the other hand, there's this observation due to Chabauty, which says, what if this is the picture over the complex numbers in the complex topology? What if we instead, I'm still being recorded, right?
Yes.
Okay, great. What if we instead work over the p-adic numbers? So this is the second question I asked. Over the p-adic numbers, if let's say I have, for example, a cyclic subgroup of this Jacobian, this looks now like some kind of p-adic manifold, and maybe I don't want to say too precisely what I mean by that, but a cyclic subgroup will really just have dimension 1. In general, if the rational points form a subgroup that are have R generators, then they'll kind of be confined to some analytic subset of dimension R. And if R is less than G, then that analytic subset will intersect the curve X in a finite set. This is the method of Chabauty. It says if you can kind of compute this finite set, then all the rational points are guaranteed to be contained in this finite set. So you get some finite set of p-adic points on the curve, and then you're guaranteed that all the rational points are contained in that set of p-adic points. I'm going to switch, keep this picture in mind, but I'm going to switch back now to my slides. Okay. So this approach doesn't work complex analytically. It does work in the p-adic topology. So this is a theorem of Chabauty in 1941. If you have an algebraic curve, it has genus G. And sorry, I haven't defined A of Q as just notation for the group of rational points of A. If this group has rank R less than G, then you intersect X, you intersect the curve inside this p-adic variety, you kind of intersect the curve with the group of rational points, and you get a finite set. And So because of that, first of all, you get a proof of Mordell's conjecture in this setting. Notice this is 40 years before Faltings proved Mordell in general. And second, that this is maybe something you can explicitly compute. You can compute the embedding of x into its Jacobian. You can compute, at least, let me say this carefully. In practice, you usually often can compute the group of rational points on an abelian variety. As I recall, maybe it's not known whether you can do this kind of algorithmically in full generality, but in practice, you pretty much always can. And so you can compute this intersection. And if you're lucky, this actually gives you exactly the set of rational points. So I'd like to say a couple words about sort of the limitations of this method. What exactly does Chabauty's method get you? First of all, you need R to be less than G. Remember, R was kind of the rank. R tells you how many rational points you have on the Jacobian. If the Jacobian has too many rational points, this method just doesn't get you anything at all. On the other hand, maybe there are heuristics that mean that kind of suggest that most abelian varieties should have rank 0 or 1. So maybe kind of it'll very often happen that R is either 0 or 1. G, of course, is at least 2. And so often you hope this won't be a problem. On the other hand, there are also like lots of curves of interest where R is greater than or equal to G. And then you're out of luck. Okay, the next thing that could go wrong, I said you take this intersection and that's going to contain all the rational points. So in practice, what you do algorithmically is you go searching for rational points. Typically, if you have a curve, kind of all the rational points usually often have very small coefficients. So you kind of find them all very fast. They all have coefficients, less than 100. You search up to 1 million because you have a fast computer. Why not? You don't find any between 100 and 1 million. You say, okay, I think I have all of them. Then you go and you do this p-adic thing, and you already have your list of, five points that you conjecture is all of them. You do this p-adic thing, you run the Chabauty method, and you get a set of 7 points, 7 p-adic points. 5 of them, of course, are the 5 points you found before. And you have these 2 extraneous points. Well, now what do you do? And sure, you can go searching. I mean, now you have, p-adic approximations to these 2 points. You can go searching even higher for rational points that are, p-adically close to that. But maybe they're just really extraneous intersections. Well, when that happens, there's things you can do. There's something called the Mordell-Vasiv. There's also just the kind of dumb option to change p and try again. I said we're working p-adically. You can choose any prime number p, so try a different prime number p, see what happens there. So in practice, this Chabauty method is very useful. And it's kind of, as soon as you have a curve that's where R is less than G, you kind of expect that you'll be able to play around with the Chabauty method and kind of fudge it a little bit, and eventually you'll get a proof that you have the full list of rational points. I realized a second ago I skipped a slide on sort of Coleman's improvement to Chabauty's method. This is sort of a technical device. Chabauty's method is I drew this really nice picture on my tablet a second ago. Here you have the Jacobian, here you have the curve, and here you have the rational points. To make that work computationally in practice, you actually kind of need to be able to compute with Jacobians. Like I said before, the embedding of the curve in its Jacobian is kind of given by integrating different algebraic differentials. And so Coleman developed this theory of p-adic integration that lets you make sense of this differential and gives you kind of a computationally efficient method for computing computing coordinates on the Jacobian. And so Chabauty's method with using Coleman integration is kind of a very powerful modern tool for rational points on curves. Any questions so far? Okay, great. I'd like to say some vague words about kind of more recent work. The subject of rational points on curves has kind of been very active lately. And of course, that's not because of Chabauty-Coleman, it's because of kind of more recent work of Min-Young Kim. So Kim's method, sometimes it's called non-abelian Chabauty or Chabauty-Coleman-Kim, offers kind of a generalization, a more powerful generalization of Chabauty's method, where you replace the Jacobian with the series of maybe higher Albanese varieties. So maybe the first of these varieties is supposed to be the Jacobian, and then you have this kind of infinite sequence of varieties of higher and higher dimension. Your curves embeds into each of them, and the idea is that each step in the sequence, each step in this Kim tower will kind of give you a stronger and stronger obstruction to the existence of rational points. So even when the Jacobian, if R is greater than or equal to G, the Jacobian has so many rational points that you can't say anything about rational points on the curve. But when that happens, you just move up to the second step in Kim's tower, or the third or the fourth, and it's expected that eventually you'll be able to deduce finiteness of rational points.
Is there a theorem of that sort that, right? I mean, Faltings tells you that there are only finitely many. I mean, is there a guarantee that when you shove Faltings into this perspective that it's going to be a level at which it's got to work? Conditionally
on various conjectures. So Kim proves that if you assume the Fontaine-Mazur conjecture, it's true, that it will, I think maybe even at some fixed level, like maybe even at the third level, if you assume the Fontaine-Mazur conjecture, then you're guaranteed to kind of get finiteness from Kim's method. If you don't like Fontaine-Mazur, if you assume Bloch-Kato, it's true. If you don't like Bloch-Kato, he has maybe a couple of other conjectures, each of which also imply this finiteness. In general, it's I guess there's no unconditional.
Okay, thank you. And again, I apologize for interrupting.
No, thank you. It's yeah, I'm happy to hear it.
Could I ask one more on that?
Yeah.
Please.
So when we say that we're getting finiteness, are we still in the situation where the rank is less than G and now we just have a provable method, or does this now extend to additional cases?
Sorry, this is supposed to work for all curves when the rank is kind of greater than or equal to G, or when the rank is anything, but we're worried about when the rank is very large. Yeah. Okay. So it's supposed to work for all curves. The other kind of drawback of Kim's method is that, at least kind of the way it's originally presented, it's not really clear how to make it into something, an algorithm that you can kind of run in practice. I mean, Kim kind of works with these Selmer varieties for Galois, for Galois representations or something. I mean, whatever it is, it's some very, it's an abstract thing that's kind of hard to get your hands on, and certainly hard to get your hands on in a reasonable kind of computable amount of time. And so what happens in practice is that even the second step in Kim's tower is too hard to compute, but there's maybe an intermediate piece, maybe I'll call it 1 plus epsilon, just a little bit more from Kim's tower than Chabauty's method, that gives what's called the quadratic Chabauty method. And quadratic Chabauty is something that you actually can use in practice. It's kind of, at least that tiny piece of Kim's tower is something that people have made explicit and computationally effective and have used to find rational points on various curves. For example, where R equals G, so where Chabauty itself doesn't work. And so I refer to just one paper around here. There'll be a link on the last page where these 5 authors kind of determined the full set of rational points on a certain modular curve that had never been resolved before. It's a curve of genus 2, the Jacobian R equals 2. The Jacobian kind of has a rank 2 group of rational points, so Chabauty's method doesn't work. And kind of all the standard toolbox they tried before didn't work either, and this variant of Kim's method actually worked. And with an awful lot of algorithmic work and computer programming, they managed to solve the problem. And I have, maybe I won't say much about this, I have some work with Akshay Venkatesh that also kind of hints at another p-adic, possibly an algorithmic approach to this computational Mordell conjecture that again kind of works by some sort of p-adic methods. And I'd like to say also a little bit about this is work in progress with Levent Alpoga. We're hoping to show that there exists an algorithm conditionally on conjectures that maybe people believe that will solve the Mordell problem for any curve for any curve of genus at least 2 over, I write over cube, but in fact it's over any number field. And so sort of more specifically, because I said the algorithm is conditional, I want to say exactly what part is conditional. This algorithm, it'll be something that you could maybe turn into a computer program. And what happens is the program runs and runs and runs and runs and runs, and maybe eventually it stops. If it stops, it'll give you a list of rational points, and it has proven that those are all the rational points. So if it stops, you can completely trust its results. And meanwhile, if you assume these various conjectures in arithmetic geometry, then you know the algorithm will eventually stop. So this sounds like a really great thing that you could kind of write a program and kind of run it on your computer in practice, because even if because the end result is independent of these conjectures. All you need the conjecture for is to tell you that it stops, but once the program has stopped, you actually know you have the full list and you're done. And so that's really great. And so this sounds like, well, I want a copy of that. But sort of the other problem with this algorithm is it will be so terribly slow that it seems like there's not really any hope that it'll ever stop in practice. So it'll stop, but you kind of have to do some searching for very, very large number fields. And so maybe the amount of time it'll take to stop is some sort of double exponential in G times some other stuff. And so in practice, it won't stop. So anyway, this has the status of theorem in progress. So I guess once it's written up, it's true. And right now we think we'll be able to write it up. I'm almost done. I just want to sort of say, this is a colloquium, so I don't want to say anything too specific here. But what goes into this more modern work of Kim and my work with Venkatesh and this potential algorithm? There's kind of a lot of high-powered machinery. We work with Galois representations. There's sort of p-adic techniques that come in. There's p-adic cohomology theories. If you've heard of crystalline cohomology, that's what I'm talking about. I mean, there's some sort of p-adic cohomology that lets you kind of see an action of Frobenius on cohomology. There's p-adic Hodge theory that kind of links the Galois representations to the p-adic cohomology theories and so forth. There's kind of a lot of high-powered stuff. Maybe I'll take one more second and just name kind of one other idea that goes into some of this, because it's kind of a pretty idea. So let me share the other screen again. This is, I guess, Parson's trick that I'm about to tell you about. If I have a hyperbolic curve X, over the complex numbers or any number field, or any field, then you can build a family of curves whose base is X. So in other words, what's going on here is Y is a surface, X is a curve. And when you have a surface mapping to a curve, algebraic geometers think of that as a family of curves, because for every point on X, I can take the inverse image of that point under this map. That'll be a curve. It'll be one-dimensional because Y was two-dimensional. This map kind of collapses down one dimension. That inverse image is a curve. So every point of X will give me a different curve. So we think of this as a family of curves. that are kind of parameterized by the moduli space X. And what you do to attack kind of the Mordell problem is you start with the space curve X, you build a family of curves over the base X. And now when you find a rational point of X down here, that's also giving you a curve up here that's defined over Q. So this is kind of a an idea that goes into a lot of these attacks to Mordell's problem. Anyway, I think I'm gonna leave it at that. Let me share the previous screen just so I can show you the list of references. And I'll open it up to questions.
So, oh, maybe I'll turn off the recording.